Okay, now we want to know the following. So let's say here's a massive object and you throw a tennis ball at it. Okay. Or this could be the sun and this could be the earth. This could be a planet, it could be an asteroid or whatever. And you want to know what kind of orbits are possible around this object. Of course, if you throw it straight at it, it'll just fall into it. You know? But we're not going to do that. Okay, so what kind of orbits are possible? Okay. An orbit like this is called a bound orbit. Why is it called a bound orbit?
Object can't leave on its own.
Yeah. So if it's going in an orbit like that, it'll be there. It'll be going like that forever. You can come back 3 billion years from now, it'll still be going like that. Yeah. It could go like this. It could go to infinity. Okay. So, so here are the possible orbits. Okay. All right. It turns out that this guy is a bound orbit. For you to have a bound orbit, the total energy of it, which is potential plus kinetic energy, needs to be less than 0. This is a parabolic orbit. Total energy is 0. Okay, so you throw a ball like that, it will go to infinity, but when it gets to infinity, its kinetic energy is 0, potential energy is also 0. Okay, so it'll go to rest. So it's like going to infinity and dropping a tennis ball. As the ball comes close to the earth, it's speeding up, and then it'll go back to infinity and have 0 kinetic energy. This is a hyperbolic orbit. And for that, E is greater than 0. So for this orbit, you have to go to infinity, throw the ball, and then it'll swing around the earth and go back and have kinetic energy, non-zero kinetic energy. Okay? All right, so the orbits around this object, and as long as the force is inverse square, meaning 1 over r square, the force is that, these are the possible orbits. And interestingly enough, these orbits are sections of a cone. Okay, you can have circular orbit. An elliptical orbit is a section like that. Okay. Here's the parabolic orbit. And here's a hyperbolic orbit. Okay. So the 3 types of possible orbits around a central mass depends on the total energy of the object. If the total energy is less than 0, it's a bound orbit. If the total energy is 0, it's a parabolic orbit. And if it's greater than 0, then it would be a hyperbolic orbit. So what kind of orbit does the International Space Station have?
Circular?
It's a bound orbit. So the total energy is, okay. What kind of orbits do all satellites have? Bound orbits. Okay. All right. All right.
What does that mean, energy, total energy is less than 0?
Well, all electrons in an atom, their total energy is less than 0, and they're bound to the nucleus. Okay. So the total energy of this electron in the ground state in the hydrogen atom is 13.6 electron volts. So that is to ionize the hydrogen atom, meaning to send this electron to infinity, you need 13.6 electron volts. So in chemistry, when you study ionization energy, that's the total energy of the least bound electron. Okay? All right. So Mr. Kepler, of course, studied planetary orbits around our sun. Okay, and okay, so bound orbits are either circular or elliptical. Okay, stuff happens in random in nature. Okay, the likelihood of having a circular orbit compared to an elliptical orbit are a lot less. Okay, because this is a precise section. Any random slice would tend to be an elliptical orbit. Okay, so most planetary orbits are elliptical orbit, and that's Mr. Kepler's first law. Okay. Kepler's second law, he just observed this. He didn't know why this was happening. Kepler's second law says the following. Okay, let me get a better picture. Okay, Kepler's second law says the following. If here's an object, here's a planet going around the sun, it will sweep out. So here's the radius vector sweeping out this area. So let's say it goes from here to here in 1 week. And in another week, if this is another week, this area is equal to this area. So Mr. Kepler says a planet will sweep out equal areas in equal time intervals. Okay? That's Kepler's second law. This is a consequence of the fact that angular momentum is constant. And angular momentum is constant for any central force. So if the force is acting towards the center of the object, which it is in this case, the gravitational force, angular momentum will be constant. Okay? So Kepler's second law is a consequence of the fact that angular momentum of this orbiting object is constant. Kepler didn't know this. He just observed that the planet swept out equal areas in equal time intervals. Okay? And third law says the square of the orbital period of any planet is proportional to the cube of the semi-major axis. So what he says is, let's say they're a circular orbit, it's a constant, and it's the same for all planets. Okay? In fact, this is related to this mass about which you're orbiting. So this is the period square of all planets divided by the radius cube is a constant, and that constant is this. That's the mass of the sun. Okay, so I want you guys to go home and do the following. How long does it take for the Earth to go around the sun?
365 days.
In 1 year. You'll put that in there. How far is the Earth from the sun?
1 astronomical unit.
150, almost 100 million miles, 153 million kilometers. Look it up on Google, on the web, put those numbers in there, and calculate the mass of the sun. So here you have a formula to calculate the mass of the sun. How long does it take for the space shuttle or for the International Space Station to go around?
90 minutes.
90 minutes. You could put in 90 minutes. You know the radius of the Earth, which is 4,000 miles. You can get the mass of the Earth. Okay. At the center of most galaxies, they have huge, massive black holes. Okay. So let's do it. So they have massive black holes. You can observe these stars and measure their radius. Okay. You can measure their periods, measure their radius, calculate the mass of this massive black hole. So if you have any object orbiting another massive object, you measure the period and orbital radius, and you can get the center mass. Okay, that's Kepler's third law. Okay, so those are Kepler's three laws. You can read the rest. Okay. So what Mr. Newton showed was if the force between these two guys is central and it's G, it's if the force is G r squared, it's inverse square law, then you get a closed orbit. It'll be an elliptical orbit and the object will go around like that forever. Yeah. Now, it turns out that Mercury's orbit does not close, and the effect is very small. So it's actually spiraling like that. Yeah. What this means is, what this implies is this force is not that. The force of gravity between the Sun and Mercury is not that. There's a small correction. And that's what led to, well, so when Einstein came up with a better theory, improvement on this guy, this is the first thing he calculated. Okay? So when Mr. Einstein came up with the general theory of relativity in 1916, this is one of the first things he calculated, the deviation of Mercury's orbit from an elliptical orbit. Okay. Okay, so I've shown you how to calculate the mass of the Sun. You can use the orbital period of the Earth and the orbital radius of the Earth. This is about 100 million miles, 93 million miles, 1 year. Again, you got to put it in appropriate units. Yeah? So, mass of any object being orbited can be found using the orbital radius and the orbital period of the object that's orbiting it. All right, we depend on satellites quite a bit. Okay, so here's a satellite orbiting Earth. Okay. And what this gives you is the orbital speed of the satellite. Okay, so the orbital speed of a satellite is g times the mass of the Earth divided by the distance from the center of the Earth to the power half. Okay. So the centripetal force is being provided by the gravitational force. A geosynchronous satellite. Do you guys know what this is?
It maintains a constant relative position to Earth,
Yep.
whatever's below it.
Mm-hmm. All right. I'll be back in a second. This is important for you guys to see. All right, so the Earth, of course, is spinning and it goes around once in 24 hours. So let's say if you have a satellite that once went around once in 24 hours, it can potentially be in a geosynchronous orbit. Okay. So this takes 24 hours. This guy also takes 24 hours. This guy also takes 24 hours. Okay, so from this formula, you can calculate the distance for which you have the appropriate speed that it takes 24 hours. Okay, so you can put this in and calculate the radius and the velocity. Okay, so if you are 42,000 kilometers above the surface, above the center of the Earth, from the center of the Earth, if you're that far away, that is 36,000 kilometers above the surface of the Earth, you go take 24 hours. It doesn't matter what inclination you have. Now the Earth is spinning like this, so if you're right above the equator of the Earth and rotating in the same direction as the Earth, that is a geosynchronous orbit. Then you're right about the same point of the Earth. And why is that useful? Because this satellite is exactly there. You can bounce off TV signals and make all kinds of money. Okay. In fact, this is the most expensive parking spot on the planet. Okay.
In theory, what if you weren't around the equator? What if you were like closer to one of the poles?
No, you can bounce off.
No, I mean like in terms of the orbit, would that change?
I'm
the
sorry?
Orbit? Would it still be the same orbit, or would
Okay,
it
start
change?
over again. Start over again.
If the satellite was not in orbit like directly in front of the equator, but it was like closer to one of the poles like north or south,
Yeah, then
how
it.
does that impact its like orbit?
Then, well, I mean, if you're at that distance, you'd still take 24 hours, but the point under the Earth rotates away from you. So, okay. All right. So. All right, so here they show you all these parking slots. Okay, and they're assigned to countries. Yeah, so that's the most expensive parking spot. And there's right now about 720 spots every half a degree. Okay? And you can put multiple satellites. How can you put multiple satellites on the same spot?
Half a degree's massive.
So if you're talking in different languages, it does. Okay. So if you send a beam, if you're talking at different frequencies, then you can. Okay. All right. So you know what a geosynchronous satellite is. So here is the kinetic energy of a satellite, and here is the potential energy of a satellite. Okay. What is this total energy equal to? Is it greater than zero, less than zero, equal to zero?
Less than zero.
So it's a bound orbit, it's less than zero. You know? There's the total energy. It turns out that kinetic energy plus potential energy can be shown to be equal to that, 1/2 the potential energy. Okay? And for a circular orbit, it's that. For an elliptical orbit, it's that. Okay. The U.S. military tracks all objects bigger than a baseball. You know? There's about 500,000 of those objects out there. Functional satellites, there's a lot of debris out there. You know? So these are the geosynchronous orbits. So, all right, that covers the concepts from this chapter. I can tell you about some stuff. Okay, so here are three interesting topics. I can tell you about tides. Okay, so I can tell you about tides. We can talk about the theory of general relativity, or so that would cover dark matter and all that. Or I can talk about gravitational waves. So we'll spend 5 minutes on each one of those topics. What is it that you want to hear about?
Did I hear dark matter?
Huh?
Did I hear dark matter?
You want to hear about dark matter? The gravitational waves is more sexy. You still want dark matter? All right. All right, we'll do both because you gotta hear about gravitational waves. All right, we'll go real quick, okay? So here's Newton's law of gravity is the following: G(m)(m) by r squared, and I'm just going to basically tell you little snippets, fun snippet. Okay, so here's the Earth going around the sun. And if you ask Mr. Newton, I mean, he was a very smart guy, but still, if you ask him this, okay, let's say I go home and make the sun vanish, what will happen to the Earth? So Mr. Newton couldn't answer this question. Okay, so for instance, I'll give you another sort of illustration. Let's say you've done this, you tie a tennis ball to a string and whirl it around. If the string breaks, what will happen? The tennis ball will go straight. When will it go straight?
The instant it's released?
The instant the string breaks. Okay, so now let's come to this question back. Okay, I make the sun vanish, the Earth will go straight. When will that happen?
8 minutes after?
8 minutes after. Okay, so that's the correct answer, but Mr. Newton couldn't answer that. But wait, why 8 minutes? Why not instantly?
Because gravity moves at the speed of light.
Okay, so here's Einstein's answer. Okay. All right, if you have no matter or energy, or space-time is flat. And then you go by a star, it curves space-time. And Earth, okay, if there is no force acting on an object, what will it do? You played air hockey. If you push the ball and then there's no force acting on the ball, what does it do? It's going in a straight line. When no force acts on an object, then it goes in a straight line. Okay? So now in curved space-time, with no other force acting on it, this object is going in a straight line. So when the Earth is going like that, it's going in a straight line. Okay, now you go and make the sun vanish, the space-time is going to start getting flat. And it becomes flat where the Earth is in 8 minutes, and that's when it starts going in a straight line. Okay, so that was a complicated answer, and it took Einstein, so that answer we got 250 years later. Yep. So what this is telling you is, this fella is matter and energy, how they're distributed. And this guy tells you how space-time is curved. Okay? And these guys are related to this guy. Okay? So this is Einstein's theory of general relativity. What it tells you is space-time tells how matter curves. Okay? And then the curvature of the matter tells other tiny objects how to move about. Okay? So that's Einstein's theory of general relativity. Okay? And of course, black holes are object where the escape velocity becomes the speed of light. So, by the way, the radius of the Earth of the Sun is about 700,000 kilometers, and if you squeeze the Sun into a radius of 3 kilometers, okay, so you got to squeeze it quite a bit, the escape velocity from the surface would become equal to the speed of light, and it'll have turned into a black hole. Okay? So if you squeeze the Sun into 3 kilometers, 3 kilometers is roughly from here to US1. Okay. Now, of course, as far as we know, once you squeeze it within that, it will keep falling. We don't know the correct picture to answer. So as far as everything will collapse to a point, but we know that's not the correct answer. Okay. You want to turn Earth into a black hole, you would have to squeeze it to that size. Okay. So you squeeze the Sun within this radius. This is called the event horizon, okay? And it's the Schwarzschild radius. Well, all the stuff has fallen to the center as far as we know. But if you try to escape from here, the escape velocity is greater than the speed of light. On the event horizon, the escape velocity is the speed of light. Here, it's less than the speed of light. So if you're here, you can potentially escape. If you're here, you can't escape. Okay? And if you fall within the event horizon, you're in a different part of the universe. This part of the universe cannot communicate with this part of the universe. Okay? All right, so if a lot of stars happen to be binaries and stuff like that, we are unlucky that we have only one star. Okay? But if over time, as this star evolves, it can expand, and if it expands and this stuff gets too close to this guy, he'll rip stuff off. So this is a companion star. This happens to be a black hole, and he'll rip stuff off. That stuff will fall in an accretion disk. Okay, it'll get hot and stuff like that. And if this guy is not a black hole, let's say he's a neutron star, this stuff falls in, and if this all falls in and he becomes more than 3 times solar mass, then he'll turn into a black hole, okay, and so on. Actually, and so, all right. So all kinds of fun stuff can happen. Okay. By the way, so when the mass of the star is less than 1.4 solar masses, then he becomes a white dwarf. A neutron star, if the mass of the star is between 3 solar masses and 1.4 solar mass, and it's a black hole if the mass of the core of this is greater than 3 solar masses. Okay. And so if this is a white dwarf and this stuff falls in, and when the mass gets to be more than 1.4 solar mass, you'll have a supernova explosion. Okay. So here's an accretion disk around a black hole, and some of this material can escapes along the jets. So okay, here's a pretty picture. Not a pretty picture, it's a nice, okay. All right, so light travels in straight lines, but if you have a strong gravitational field, light can bend. Okay, So let's say here's a star, and if this star light is skimming the sun, it gets to you, and you are hardwired to think that light travels in a straight line, and you would see the image of the star there. The star is actually here. Because the light bent, you're seeing this image there. So the sun's gravity bent this light. Are there stars in the sky right now?
Yeah.
Why aren't you seeing them?
Sun's brighter than the
Huh?
stars. Sun's brighter than the stars.
Yes, so how the heck are you going to verify that Einstein was right? He's saying this.
You look from space.
Well, the sun is still there.
Eclipse.
So that was they were chomping at their bits for the first eclipse. You're going to block out the sunlight. All right, so you had taken a picture of this sky 6 months earlier. The star was here. Okay, so this star was here relative to further out stars. And then during the eclipse, you took another picture of that same portion of the sky. And instead of being here, that star was here now. So you verified Einstein's deal, prediction. All right, here's a quasar. Okay, and if you have a massive galaxy here, there's the Earth. This light bent like this light bent like that. And you're hardwired to think that light travels in straight lines. So there's an image formed, there's an image formed. So for the same object, you have multiple images formed. So here's a picture. You took a picture of the sky. Okay, so you're seeing two quasars. Well, how do you know if it's the same quasar or is it two different quasars?
You check its signal.
Huh?
You check its signal.
What do you mean check its signal?
Thing, you look at one and see if it matches the signal or the chemical composition of the other.
Well, all chemical compositions are essentially
Well, I
just.
mean the exact.
Okay, yeah. So, okay, well, you're right. I was just pushing you. All right, so what you do is you look at the intensity of different colors. Okay, and for every object, that curve is unique. And if the curve is the same, then it's the same object. Okay. So it turns out they're the same objects, multiple images. Okay. Let's see. Okay, so again, these are the same objects. These are the same objects. So you see, intervening mass is bending the light. All right, what is this image? What is that blue stuff? All that blue stuff is dark matter. Okay, we have this image formed and there's no intervening mass that's producing those images. So all the blue stuff is there. That's the calculated mass out there that we can't see. So in fact, the composition of the universe is, this is roughly 70% dark energy, 25% dark matter, 5% normal matter. Look at this. This is crazy. This is what we know. Dark energy is, why is it called dark energy? Because we don't know its nature. We are in the dark and we're calling it dark. What is this dark matter? We don't know the nature of the matter. We are in the dark. So 95% of the universe, we don't even know what it's made of. Yeah. All right, guys. All right. 3 minutes of the best experiment ever done. All right. Okay, so we depend on electromagnetic radiation. I mean, this thing wouldn't work without electromagnetic radiation. So if you want electromagnetic radiation, what you do is the following. grab hold of a charged particle, any charged particle, and you make it accelerate. And the easiest way to do it is just jiggle it. And you can do this with an electron. This is what a dipole antenna will do. You will learn about this in physics 2. Okay, one of the things. So here's an oscillator circuit, and anyway, oops. So you jiggle this charged particle and it'll emit electromagnetic radiation. Similarly, you take a mass and jiggle it and it'll emit gravitational waves. So here, I'm emitting gravitational waves. Any mass, okay? I'm emitting gravitational waves. But there's no way in hell you're going to detect that. Now, if you grab hold of a black hole and jiggle it, this you might be able to detect. How the heck are you going to jiggle a black hole?
Hitting it with something heavy.
All right, so what you do is, I just told you a minute ago that most of the stars out in the universe are binaries. So you get this black hole to be jiggled by another black hole. They're going around each other, and that's essentially jiggling. So now these guys will emit gravitational waves. Yep. All right, so here's two black holes going around each other, and they're emitting gravitational waves. Okay, and as they emit gravitational waves, energy is being carried away, and so they're getting closer and closer. Okay, and eventually they'll merge, and then they won't emit any more gravitational waves. Okay, so this kind of stuff happens all the time. We've been looking for gravitational waves for about 70 years, and 2015 was the first signal we detected. Okay. All right, I'm going to set you guys up just so this was an amazing event. Our sun is 5 billion years old, and it's got another 5 billion years to live. So our sun has a lifespan of 10 billion years. And I'm just giving you rough numbers. So let's say when it was born, it was 100 pounds. And when it dies in another 5 billion years, it'll weigh about 98 pounds. What happened to the other 2 pounds? I'm sorry? So the fusion reaction going on, okay? The sun is emitting energy. So over the 10 billion years, all the light it emitted amounted to 2 pounds. Okay? So it'll lose 2% of its mass over 10 billion years. Okay? When these two black holes were going around each other, this was about 30 solar masses. Now the 30 solar masses, 29 and 35, something like that. Okay. So they were spiraling around each other, and in the last 200 milliseconds, in the last 0.2 seconds, they radiated about 3 solar masses worth of stuff, energy. The amount of energy radiated in those last 200 milliseconds was 100 times greater than the energy being radiated by all the stars in the universe. Let me state that again. In the last 200 milliseconds, the energy power radiated was 100 times greater than all the stars being radiated. So if you could see in the gravitational lens, if you could see gravitational waves, it would be the universe would have been 100 times brighter in the for that 200 milliseconds.
That's kind of insane.
That is more than insane. And then we barely detected it. Yep.
So is all the energy being emitted as like a gravitational wave?
Yep.
It can't-
Mm-hmm.
Is that the only way that? Because that's the only way.
Well, that was the main way it was in it. So how do we see this? Did you guys understand the problem? I mean, do you guys understand the magnitude of the event? All right, so how do we see it? Okay, so here's what happens. So here's the detector. This is in Louisiana, and okay, so let's say you have a spear of balls like this. Okay, and when a gravitational wave passes by, so here's the spear, and a gravitational wave passes by, the spear gets elongated like that, and then it'll come back there, then elongates this way, and then come back there. Okay, so what I'm saying is, so here was a circle, it becomes like that, and then elongates like that. Okay, so that's what's happening as the gravitational wave is passing by. Okay, we are going to detect that. Okay, you know how much it changes? 1 meter will become, so the radius of 1 meter will become this will become 1 meter plus 10 to the minus 21 meter for the event we detected. The size of the nucleus is 10 minus 15 meters. The size of a proton is roughly that, okay, 10 minus 18 meters. You're going to detect this change is that the Earth-Sun distance is 100 million miles. When the gravitational wave passes, the Earth is going to move about 1 atom width. And you're going to detect that. The distance between the Earth and the closest star is going to change by the size of a football.
How is that even detected?
There you go. There you go. I wanted that to sink in. It's just mind-blowing. All right, so now you guys understand? Okay. So how are we going to detect it? So here is the instrument. This is called an interferometer. Okay. Okay. So here is the basic idea. Okay, so here is a light beam. Okay, those are the crests and troughs. And if you have another light beam coming such that the trough matches the crest, what will you see there? This beam will exactly cancel this beam. Okay, and you have a dark spot there. Now, if this beam is slightly off, now there will be light there. Okay. All right, so this is dark, this is light. Okay. So here's what you're going to do. All right, so this is about 4 kilometers. This is about 4 kilometers, 4 kilometers. These are evacuated tubes, the best vacuum in the universe. Okay, so they've set up this, they split this beam and the beams travel back and they come back such that they exactly cancel. And it's dark. Okay. So the normal setting is you have perfect cancellation and it's dark. Now if a gravitational wave went by, this length would get longer. And now you don't have perfect cancellation. Okay. And so when the wave goes by, this initially gets longer, and then in the next cycle, this gets longer, and so on, and you don't have perfect cancellation. So anytime you see a light, then something happened. Maybe a gravitational wave went by. Well, a truck drives by, you get light. Truck will do the same thing. So how the heck do you know if it's a gravitational wave or a truck?
You quarantine the area.
So what you do is, it took you $10 billion to make this lab. So you spend another $10 billion and make another lab there. So when the gravitational wave goes by here, you get a signal, and you get the exact signal there, and that was a gravitational wave. Yep. So here was the signal that was detected in. So here was the signal. Okay. This is no light, this is light. Okay, that was the signal detected in 2015. Okay, the black holes were going around about 100 times a second at the speed. This massive object was traveling at 60% the speed of light. Okay. All right, guys, so we'll stop here.